Hello, good evening, and welcome to episode 39. Episode 39 of Codebase Alpha. We're certainly getting through these episodes now. So this evening we're going to be doing some more work on the synthesizer. And the main aim today is to get what we call a phasing effect, a phaser. It's not a Star Trek weapon, it's a digital effect that we're going to try and to code. We've got a fallback position and we've got somebody else's code we can fall back to if we get stuck, but I'm trying not to use that. Good evening, Faberius. Welcome to the stream. Good to see you. Nice to hear you join. Thank you very much. As I was saying, so the main aim is to try and get this phaser effect onto the synth. Now, I've done a little bit of work on the synth as well, off stream. Not very much, just a little bit, just to kind of practice creating these effects. Oh, you haven't seen the scene? Yes, this is my control. This is Codebase Alpha control room, Fabarius. So this is, I think Alf. He sits there, in that seat there. But yeah, I'm in the command seat here. And as I was saying, I've done a little bit of work on the Brandonius. Welcome. This is the Star Wars. Yes, I've got my Star Wars shirt on. It's got a bit of it's got a bit of green in there, so there's a bit of interference on it, so I'm a bit see-through in places. So welcome, Brendan. It's good to see you. Thank you for joining. So where was I? I've forgotten where I was. Rick Ardopi. Hello, welcome. Thanks for the stream. Oh, so you were working on the bot framework. Oh, great. I'm glad you've popped in. So yes, it was fine. I hope you can get on with that, because they kind of Microsoft pulled the rug from under me really when I started that project. I started it in 1 week, and the next week they'd changed the framework. Well, they changed the project structure. The framework was largely the same, but they changed the project structure. So I've not yet caught up with their changes. I don't see much point. It works fine as it is. But yeah, if you go back in, you go to the GitHub, and if you start from the where I started, which is just the Echo bot, that version, then you should then you should be fine to work from that. Claire Darth, welcome to the stream. Good to see you. My name, well, I'll go by the handle SNB, but my name's Stu. So yeah, so that's fine. You can call me by either. So okay, I'll just try and recap where I got to. I forgot where I got to. So yeah, I was saying that I did a little bit of work on the synth, not too much, but I did want to practice. I want to practice creating one of these digital signal processing applications that we kind of plug into our we plug into our synthesizer. So we've got one of those to show you. We've also got a pull request from FuelSnable, which we'll get to straight away, I think. So let's drop over into the code and actually sort out this pull request, because it's a nice little one which will be useful for us today. So let's go over to GitHub, and the pull request is here. And FuelSnable has basically is beefed up the power of our T4 template that we use to generate part of the view model for our WPF application. So as you might recall, if you've followed on before, the T4 template can be used to create commands and to create properties. And what FuelSnable has basically done is to extend it so that where we've got labels for properties, then it will generate those. Yes, so Brendan, T4 templates and FuelSnable, they don't go together at all, do they? Yes, they do. Cody Beard, welcome to the stream. Good evening. Thank you for joining. So yeah, so he's put this pull request in, and I've already kind of reviewed it off stream. So 3 files have changed. The generated view model obviously has changed because it ran this new T4 template against it, so it's changed slightly. So that's that huge file with all the changes in. So they're just changes in the generated file. Then in our T4 template, we now have these LP properties, which are label properties. So, for example, for the attack, the decay, sustain release, cutoff frequency, Q value, etc. So this is going to save us a lot of time in setting that up. Was Weetold? Did Weetold join? Oh yes, Weetold. Good evening. Welcome to the stream. Yes, yes. But I mean, Fuel Snowball kind of got in there with his T4 templates, and I'm really grateful because they my focus isn't particularly on WPF in this project. So this is my very first WPF project ever. So I'm very grateful for not having to think about a lot of those more mundane aspects. The T4 template really takes it away from me. And yeah, so what else have we got here? We've also got so this is some code here to create the dependency between the frequency and the new feature is the frequency multiplier, which I'll show you. So let's approve these changes and just bring this straight into our project. So we'll merge this pull request. Slayer, did you hear that Aston Martin is working on creating 25 custom-made DB5s with some Goldfinger gadgets next year? What, with ejector seats and machine guns? That'd be good, and oil slicks. That'd be fantastic, wouldn't it? I don't know if anyone in the UK did caught the new series of Top Gear, which started on Sunday with Freddie Flintoff and Paddy McGuinness and Chris Harrison, which is kind of a bit of a rebirth of that program. Really, I really enjoyed it. So I don't know if that's kind of made its way over to the States at all, but yeah. Fuel Snowball, welcome. We're just about to merge in your pull request. So thank you, Rick. Thank you for popping in. Yeah, do pop by again. And it's good to see you. So thank you for your kind words about the bot framework streams. Okay, Cody Beard, you don't have a TV? Wow. So Brendan, Top Gear is popular in the States, is it? Well, I think it was. Well, see, without Clarkson, yeah, I must admit, I do like Jezza and Captain Slow and Hammond, such is why I do watch the Grand Tour as well. But yes, the post Clarkson series I didn't particularly like, but this is a bit of a rebirth, so I'm really pleased that it's come back strong. Okay, let's merge this pull request in, and we'll pull this change down. Yeah, Top Gear pre-Clarkson was actually a motoring program, wasn't it? Rather than a comedy show. Thanks for this very useful contribution. Okay, so let's go and pull that down. So we'll go. I'm going to use Visual Studio for all my interactions with Git this evening. Cheers, everybody. Okay, so we've got that now. Here's our new T4 template, and you can see you've got the label properties, so they combine the label, which is here, and the actual property themselves. And we're going to be using this quite a bit this evening. But let's not look at that at the moment. Okay, so what I'm going to do is I'm going to run up the synthesizer and just show you the first of the changes I've made. And this is around our tremolo control. Cody Beard, it's 10 years since you last had a TV. I don't think I could kind of survive without my TV. Yes, Fuel Snowball, it's a great PR. Thank you very much. It's going to be really helpful. So what I've done with the tremolo control, I've renamed it tremolo/AM, and I've got this frequency multiplier slider here. Now this change came about because I was reading in my audio programming book about some older synthesizers that used to use amplitude modulation, as a way of kind of tweaking sounds of the oscillators that produce, the basic frequencies. And I thought, well, it'd be nice to have a play with that and see what happens. So at default, if we switch on, so this is a note. This is the note A played just as a sine wave. So you can see you've got the fundamental frequency here, and it's a nice stable sine wave. If I put in the tremolo effect, so what this is going to do is basically it's going to modulate the volume. So this is the equivalent of if you were to kind of take the volume control of your TV or of your stereo or whatever, and just move it up and down at a low frequency. So currently the frequency is set to 5 Hz. So 5 times a second you're going to wiggle the volume knob. So you'll notice that what happens is we get some amplitude shifts. So this is that tremolo. Okay, it's not vibrato. Vibrato is a change in frequency. This is a change in amplitude. As you can see, it's wobbling up and down. And what this is doing is giving us some higher frequencies. You can see the spectrum analyzer is showing the fundamental here, but also a set of other frequencies. Now it turns out that if we actually boost this frequency over 20 Hz, and 20 Hz being the lowest frequency that humans, generally speaking, can hear, then it starts to have a different effect. Instead of producing an amplitude wobble like that, it produces what we call sidebands. So it'll produce frequencies either side of the fundamental. So if I bump this up to 15 and we multiply it up to 450, and I play now, you can see there's a sideband here, and you get now it's quite a different effect. If we bump it up even further, let's take it up to 720. Now you can see the side bands are quite noticeable. So they're all on the high frequency side. So this is our fundamental, and we've got these two side bands and a few other high frequencies pulled in. So if we actually increase the octave now and play A again, now you can see here's the fundamental here, and you've got a side band on the other side as well. And you can get interesting effects if you change it to a sawtooth wave, for example. Or a square wave. Ancient Coder, welcome. And once again, the triangle wave. So you get some interesting effects. So that's one of the changes I made. So if we just knock this back down to its default, which was 5 Hz, that's in contrast to so it's subtly different. The triangle, yes, the triangle does say very much like an organ, and because we can kind of fiddle around with our sound envelopes, so we can give it an attack, we can give it a decay, I don't know, something like that. Just reduce the main volume and give it a longer release, and with that we can so we can do all kinds of things. We increase the attack, or we can reduce the attack, make it more staccato, and we can increase the release time. In fact, we can make the release time quite long. There you go. It's a customer answer, yes. It's like the railways, isn't it? Yes. Okay, so that's the first change that I made. So it's just that, basically, yes, I will play I must play the closing count as 5 notes. So that's just the tremolo. So just to introduce some amplitude modulation, just to have a bit of fun with that. So let's turn off, and I'll show you the second thing. So to be honest, there's quite a bit of maths involved with these effects, and I didn't want to come in cold. I wanted to produce a simple effect, just to see that it actually we could actually write one. It worked, and also get used to the basic concepts of how these effects work. And so what I decided to do was build a chorus. Now a chorus is where you get some delay basically, and it sounds like more than one voice, or so a chorus of people singing, or a chorus of instruments playing. So I created a sample provider, a chorus sample provider, and we'll just have a quick look through this. So this is based upon the concept of a circular buffer. So you'll remember that the whole basis of a sample provider is so FuelSnowball could do UI show the resulting function. I'm sure we could make the UI show all kinds of things, especially when we start to mix in more oscillators. Currently there's one oscillator per note, but we're going to have 3 oscillators per note, and we're going to be able to mix in different types of waveforms into the same note. So that's coming up in the next couple of streams. We'll make a little bit of a start on the GUI side of that tonight. Nothing concrete at all, but I want to start preparing to having multiple voices, as they say in the synthesizer world. Okay, so with a one of these iSample provider classes, basically they implement the iSample provider interface, which basically means you have to have a property called wave format, and you have to have a read method which reads a floating point buffer. So this is, as I said before, if you know about streams, this is very similar to a stream read, except this would be a byte buffer, but we're a float buffer because we're dealing with IEEE floating point samples, 32-bit samples for our digital audio projects. So what the basic idea here is that we're going to take a sample off the input buffer, and we're going to pop it onto a circular buffer at a point which is not in the same position, so we're going to move it along a bit so it gets delayed, and then we're going to increment the filling pointer, and we use this bitwise AND here to make sure it kind of shifts around in a sensible manner, and also it's circular, so it ends up going back on itself. We have an emptying pointer, which is the pointer where we actually grab the samples from to mix into the undelayed samples, the undelayed buffer, and basically we modify the emptying pointer is the same as the filling pointer, but it's modified by a sweep factor, and the sweep basically it steps every time we go through this loop. The sweep changes, so we kind of we're cycling through. We're sweeping backwards and forwards through this buffer at a certain frequency. And then here we're going to do a straight mixing of the samples. So it's going to be half and half. So we have the unprocessed sample, which is called the dry sample, and the delayed sample, which we in the jargon we call the wet or the processed sample. We've got a constraint function here to make sure we don't stray out of plus or minus 1 basically, but actually when I was working on the phaser, I came across a much better function to use in this constraint, because constraint is basically if it's greater than maximum, it's just the maximum. So this is very much angular, so it's going to be if I can just draw it, this constraint function is going to basically it's going to be like this. You're going to have probably best not doing that, isn't it? Let's do it freehand. So it's going to be like that, where this is +1, this is -1. So it's got these sharp angles in here, and what we really would like to do by going to red is actually to smooth this out like that. And I'll introduce a function which does that, and those who are interested in mathematics might already know what that function is, but we'll come across it in a little bit when we do the phaser. Let's get rid of that. Okay. Yes, so if you're stable, can you generate it mathematically? I'm sure you can. I'm sure we can do a lot of these things. So this is the very simple kind of the concept of the circular pointers. The circular buffer is the very basis of the kind of delay concept within with digital audio. I'm sure there's all kinds of mathematical things we can do. So first off, music is a bit frustrating to you. You can't make you can make decent graphics just by playing basic linear algebra, but music eludes me. I'm the same. So I play electric guitar and acoustic guitar, but I'm not very good. I've spent a lot of time, a lot of effort to try and get good at it, but I don't tend to get good at it. So, and I haven't picked up my electric guitar now for a couple of, well, at least 12 months, maybe a bit longer than that. No, about 12 months, I'd say. So I get very frustrated by music, but this is kind of getting me back into it from a mathematical and a programming side. So I'll just show you my latest purchase, which we're going to be using on the stream at some point. And that's, if I can show you this, this is a MIDI controller. It's a 25 key MIDI controller, and we're going to have our synth able to be controlled not only by the keys on our computer keyboard. We're going to actually add MIDI functionality to it, so we can play it with the MIDI controller. Yes, everyone plays air guitar, and actually my air guitar is fantastic. There's silly there, but my real guitar is well, I've kind of varied. I've played quite complicated pieces of music, but I can't play them anymore. So yeah, I do enjoy strumming along. Basically, that's, I think, my favourite thing, to put a set of track on and to strum along to it. Okay, so that's the basic idea of this. So the concept of delaying your sample in a circular buffer and then mixing it back into the dry signal, but also having this sweep where at a certain frequency we kind of sweep backwards and forwards through the buffer, so it's not always predictable what the next well, it is predictable, but it's not always the next consecutive sample in the circular buffer that gets pulled out. It sweeps around in there, and that's what gives us the kind of the chorus effect. And you can see here's the sweep function. So it's relatively kind of complicated, and you know, I'm not saying so I didn't derive this from first principles, but I did have a good go at understanding where this kind of function comes from. So let's have a go with this function. We're going to pop it into our signal chain, and we're going to pop it in after the tremolo. So if I uncomment that, and then we plug, so we plug it into the fast Fourier transform sample provider that FuelStable wrote for us. This is very much like plugging in effects pedals for your guitar. So you plug one into the other in a signal chain between your guitar and the amplifier. Voight Knight, code base alpha, that will generate some aliasing for sure. Yes, it will generate some aliasing, and we do have a low pass filter to try and deal with that, and that's why one of the first things we built was a low pass filter. But you know, we're not it's not going to be the perfect synthesizer ever, and it certainly won't be perfect to start off with. So aliasing is where you get false frequencies, because the frequencies that are being generated are higher than your sample rate can cope with. So there's a sampling theory. You might have guessed there will be such a thing in digital audio. This is a theory by a gentleman. At least one of them was named Nyquist. And the general kind of gist of the sampling theory is that you should sample at twice the rate of the highest frequency that's going to be in your piece of music or your track. And so the reason why we choose 44 0.1 kilohertz as our sampling frequency, which is the CD quality sampling frequency, is that the highest frequency that humans can hear is about 20,000 hertz, 20 kilohertz. So twice that would be 40, and it's a little bit above that. If we have any frequencies that come into our waveforms that are higher than about 20 kilohertz, then what's going to happen is we're not going to our sample rate will be too low to actually reproduce those frequencies with any kind of fidelity. And what happens is we get false frequencies, we get kind of false lower frequencies get mixed in, and they're called aliases. And there's all kinds of techniques we can use to try and prevent those. We've got this low pass filter here, which is one of the ways we try and kind of filter those out. However, this low pass filter is on the source oscillators and not on the overall output. So we're probably going to need to have another low pass filter, which we're going to stick at the in our signal chain right at the end to kind of filter those things out. Michael Jolly, welcome. You're lurking while working. That's fine. Lurk and work. Good to see you anyway. Thank you for joining. So let's switch this on and let's see what happens when let's choose the middle octave here. Let's I don't know if you can hear that, so let's try a square wave. So quite a different sound. If I hold it down, you can hear that kind of sweep going on. And if I play a chord, so it kind of fills the kind of the background a lot with that kind of chorus. And what we're going to need to have is some chorus controls. And we're going to put, and if we get time, we'll put some chorus controls in tonight. In fact, should we do that? Should we start off with some chorus controls? Okay, let's have a look back at our chorus. So what I've set up is if the sweep width, which is the percentage sweep we're going to have, is less than 0.1, then basically we're going to turn our Matthew, welcome. Good to see you in the stream. Michael Jolly just Michael Jolly, thank you very much for the subscription. Fantastic. You get access to the Alps as well. She's your 2 months. Matthew, thank you for the cheer. Cheers. Thank you very much. Okay, so it's one of those days. Everything's it's all a bit overwhelming when you get things like that. Thank you so much. Okay, let's give you some hyperspatial hype. So, well, thank you for the subscription there. There's some HyperAlf. I do love this. This is the WebGL shader which FuelSnable has created for us. I do love that. And here's we'll have for the Matthew for the chair. Here's some Electric Alf, another one of FuelSnable's WebGL shaders, which is another wonderful one. I do love that one as well. Okay. So we've got 3 parameters which, as users, we can control: the sweep rate, the width, and the delay. So we'll be able to play around with those if we add them to the to our GUI. So our GUI looks like this at the moment. So one thing I did want to do before we go any further is, because of the concept of we're going to have multiple oscillators and multiple voices on our synthesizer, I want to have a tab control across the top of the screen here, so we can choose between the main voices and our kind of other oscillators. You're working on a shader right now for FuelSnable. We need to have a shader which can generate from a T4 template, and that would actually be perfect then, wouldn't it? Okay, so let's create a tab control in here, like that, and a tab item here, and the header is going to be main voice. Okay, and we can grab these pieces and just move them down right to the bottom, to there. Where did I put it at the start? That should be all right. Yes, it is all right. There's our first tab. Okay. And what I'm going to do is to put a couple of another tabs in. So tab item. We're going to have voice 2 and another one, voice 3. I think 3 voices should be enough for a simple synthesizer like this. So it's no longer that simple actually. And what we'll do is grab these grid width and column definitions, and we'll create a grid here. Come on, grid. Thank you. I'll put those in and do the same here. And then we'll also put our waveform visualizations in on each one as well. Let's pop those in there. Okay, so if I run that up, a T4 template generates a shader, yeah. There we go. So we'll be able to, on the voice 2 and voice 3, we'll be able to have controls for those individual oscillators, and we're not anywhere near actually doing that part yet. But it'll be interesting when we once you get there. So we've got our tab in, so that's really for the future. So we need to work in this area here. We've got our tremolo control. We should be able to fit in, I think, a chorus control in here. So let's move to that location. There's the frequency multiplier. There's the tremolo gain. So here we are. So what we need is, let's just copy this. No, we won't copy that. We'll copy the labels. Just pop them in at the end there. So we'll have this is going to be chorus. And we're going to have, so what were the things we need to control on a chorus? It was sweep rate, width, delay, and sweep rate. So we'll have width, sweep, and delay. Okay, so that's good. That fits in there. Okay, so we need an enable checkbox. Do we need an enable? We could have it so it's switched off by width. Okay, let's not have a enable checkbox initially, and we'll see how we get on. Okay, So now we need some sliders. So let's have some sliders. We need 3 sliders. Okay, and we're going to move them around a bit. So this one here is that one there, so let's move this in. So we're going to use them, just shove it across with a margin. So let's put in a margin of 30 on that. No, much more. 50, 55. That looks okay. And then we're just going to nudge these up a bit. 25 in there. And 20. 5. Maybe this is a bit more, 28. This is a bit less, 20. Yeah, that looks okay. Okay, so over in our chorus, we've got some ranges. So 0 is the bottom, and basically 1 is the max for all of those controls. So so this is going to be the chorus width, chorus sweep, and the chorus delay. And they're all going to go from 0 to 1. And to 1. We've got our ticks and we've got our snap to tick, which is what we want to do. So okay, so that looks okay. I think we could potentially do something with this. The one with dot, we could. Doesn't seem very. We can possibly move sweep in a bit, can't we? So let's have this 10 away from there, and this one 10 away. This is just fiddling really, but might as well try to get it looking half decent. Oops, that's the wrong one. That's 15. Chorus width, maybe 45. No, 55 was probably right for that. And then for sweep, 20. Delay, I don't know, 15. Yeah, that's fine. They're still a bit uneven, but we can sort that out at some point. And then we want some labels at the bottom. So these are going to be the labels that show the values. And one more. Oops. So we're going to have, this is going to be our chorus width. Like that. And then we're going to have chorus sweep label. And chorus delay. Okay, so these are way out of position, so let's go and move these in. So the chorus width label needs to move right in, so that's going to be at 40, no, 30. It's also too wide, so width of 30, no, 40. Oops, width of 40, and margin of 35. Margin of 40. Yeah. This one here looks pretty much right. Let's make it 15 because that's the number. And then this one here probably can be 10. Yeah, that's fine. Hopefully that'll be wide enough. Okay. Right. And now we need to go across to our T4 template. And we can basically copy these three here. So these are our labeled properties. They're all floats. Let's make it all nicely line up. So we've got chorus width, chorus sweep, and chorus delay. And they're basically going to be simple values like that. Okay, so saving this should prompt it to generate our view model for us. Let's see if that's worked. Oops, what have I missed out? I'm in the generating model here. Well, I've got something wrong. Let's go to that, is it? Oh, that's interesting. It seems to want to put a big gap in there. Let's see, spaces, isn't it? Let's have a look. What have I done wrong? There we go. That's the reason. That. There we go. Now we can run it. So wonderful, isn't it? I just really love that. So now we've got our values here, and they should go up now. Interesting, this sweep one isn't working, so let's have a look at what's going on with that one. Chorus sweep. It may just be there's not enough room for it. Let's just line all these things up again. I like to see it all line up. Generate again. Look at the generated model. So it was the sweep which was the problem. I've misspelt chorus. That's what the problem is. Just the normal me. There we go, chorus. So I've misspelt it somewhere else as well. That looks okay. Chorus sweep. Yeah, I'm stupid, aren't I? I really am daft with my spellings. There we go. It's a good job this is so quick to regenerate. Snowball, that's brilliant. I just love that. Okay, so now we've got our zeros. Okay. Right, we can close down those two now. So over in our XAML.cs, we can set some default values up for them. So let's go and have a look at the chorus sample provider. So I defaulted them to, so width we're going to default to 0, delay 2 and sweep rate 2, so we'll do that. Shall we? No, we'll just leave those alone. Let's go back here. That's not what I wanted to be, it's over here. There's our chorus. Okay, so let's go back and have a look at the code in that template. So if you're Snowball, if you're still in chat, there we go. It's the changed. This is what we want to do. Okay. So we need some partial methods in here. So this will be changed chorus width. So if chorus is not null, then we're going to want to change the chorus stop width. That will change the chorus width. I don't think we need to do anything with the low frequency oscillator, so we can get rid of that. And then we can do the same thing for the other one. So we got the sweep. Sorry if you're stable, I was just getting slightly confused, but I'm back on track now. Certainly made the putting those label things into the other one is it certainly made it. Did I call it sweep? Sweep rate. Let's make this class a little bit shorter, which is nice. And the delay. So let's fire that up and see if that makes any difference. Let's switch on. So we've got our chorus off at the moment, so let's play the note A. Let's add some width, and this is the same value as before. Got some clipping in there, haven't we? So we're definitely going to want to have that low pass filter in there. So if you're stable, he says, sounds like a theremin, Andre. Yes, it does, doesn't it? I mean, hopefully we'll be able to get it to sound like any number of instruments eventually by just manipulating all these various parameters that we've got, and there'll be more parameters we're going to add. So if you're stable, you use T4 to reduce the redundancy. You have to maintain, yeah. The redundant pattern in the code, there was as you say, just doing all those labels. So it's wonderful to just do it all in one line, and to be able to say that this label and this property are connected is natural. You can see there's quite a lot of high frequency. This low pass filter is not going to help us. This is on the actual source. So we're going to want to be able to have a low pass filter on the on the whole of the output. I think we'll do that at some point. That's nice. We got that very electronic-y chirping. So I think the original values for our chorus were it's a width of 2 and the rest is width of 3 and the rest at 0.2. So 3 and 0.2, yeah. There's lots of very high frequencies up here. So we're going to do something about that, but that's basically what we wanted to achieve for the chorus. So let's take a glug of wine and gird our loins for a phaser. Okay, we'll create the class first. In fact, what we'll do is we'll just commit those changes. Wide up chorus effect to the GUI. Commit that. Okay. So we'll start off by just creating the basic class, and then I'll talk a bit about. So I've got like 3 pages of notes here, I don't know if you can see, which kind of cover the algorithm and my thoughts about how to implement it. So I should be referring to these notes because this isn't something that I'm going to be able to kind of reel off the top of my head. So I do apologise for that, but yeah, this is all pretty new to me, and I'm pretty sure it's pretty new to you, unless you're an audiophile and been doing kind of digital audio processing yourself. But it's absolutely fascinating. So I'm really enjoying getting into it. Hence buying the MIDI controller, which is something I really shouldn't have bought, I suppose. But it was only a cheap one. Okay, so let's create our phaser sample provider. So we're going to add a new class. This is going to be called a phaser sample provider, and it's not a Star Trek weapon. A phaser or a phase shifter is basically something which it's going to produce what I hope is going to be like a swirling sound. I think it was originally actually used to spin the loudspeakers. The loudspeakers would rotate, so when the loudspeaker was coming towards you, obviously it's not the Doppler effect. You get that kind of the effect like I don't know, of a police car or whatever, that kind of pulsing, swirling effect. So that's what we're after. Whether we'll get there, I don't know, but because we're going to be using an algorithm which isn't, it's an approximation, so it's not mathematically accurate, because we need it to be computationally quick, at least as quick as we can make it. But I believe it's a valid algorithm. So we're going to implement the iSample provider, which is a standard interface which is provided by N-Audio, and N-Audio is of course the library that we're using to do a lot of our sounds. and we're going to implement that. But when we implement that interface, we get two things we have to do. We have to have a wave format property, as I said, and a read method, and that's basically all there is to it. But we can fit a few more things in. We need to have as we're creating a signal chain, we need to have a sample which we can plug in. So, and that's going to be a private read-only, another iSample provider. So iSample providers plug into other iSample providers, and we'll call that the source. And then we'll be able to say that the way is going to be underscore source dot wave format, because obviously the sample provider that we pass in has also got a wave format property. We're going to need now to have a method, a constructor. So public phaser sample provider, and into it we're going to pass an iSample provider called source, and then we're going to say that source equals source, and that's the basic setup. I think we can get rid of those. So whenever you start off doing a new digital effect for the synthesizer, you always start off with something that looks exactly like that. We pass a source in, and then we're going to, obviously this is going to result in us passing a buffer back out again, a buffer of digital audio samples. So now we need to look at in a bit more detail of what we're trying to do. So let's go over to Paint, and I'll do some terrible drawings. Okay, so if you imagine a signal, this is a signal which is passing through like that. So an unadulterated signal, so a buffer of digital audio samples which just passes straight through of our effect. This is called the dry signal. Dry simply means it hasn't been processed. What we're going to do is we're going to split that signal off and take the same samples through into a series of what's called stages. So these stages are going to, they're not going to affect the frequency or the volume of the signals, but they're going to shift the phase of the signals. So if you remember, if you've got a sine wave like this, okay, so that's this is 0 here. If we shift the phase of that signal, if we advance it, then it's going to be moved like that. Okay, and if we have two sine waves like this, they're going to add and subtract from each other. They're going to interact and produce a new waveform. And so what happens when you've got a waveform which is actually the exact opposite, it's shifting phase by 180 degrees, then obviously we're going to get destructive interference here. So this peak is exactly offset by this peak, and then we get basically a flat signal, no sound at all at that point. Then it goes, the sound's going to increase as they interfere with each other, until we get our blue signal, and eventually is going to come exactly in phase, and they're going to add together and we get double the amplitude. So we're going to be kind of affecting it like that. So it's kind of changing the amplitude, but it's not really. It's actually the phase that's shifting, and we're going to shift the phase. We're going to kind of sweep through the phase shifts, so that the peaks and troughs interact in different interesting ways at different points. So how we do that is we pass these things through these filters, these stages. I'm also going to represent them by boxes. So we have any number of these. I'll just put dot dot dot, and then another one. So there could be many of them. And when we come out of here, we're going to take this signal and we're going to mix it back in to the dry. So we're going to mix here. This is the wet signal. We passed it through these filters, and we're shifting phases. Okay. However, what we can do as well, we can kind of amplify the effect that this wave shift has by taking some of this signal and feeding it back here. This is called the feedback, and this really intensifies the effect. Okay, so this we would call this stage 1, stage 2. This would be stage N. And there's some kind of mathematical formula which go with each of these square boxes, these oblong boxes. And let's see if we can fit those in underneath. Okay, this is where we get some maths. So I do apologise if you're not mathematically mathematically minded, but unfortunately you can't avoid it. Maths is all of this is the physics of sound, physics of digital signals, digitized signals. It's all mathematical. It's all sine waves and cosines and all that. Yes, maths with an S. Maths, formulae, not formulas. So we're English, so maths. Yeah, mathematics. And if you're offended by me not saying math, okay. So if we imagine this is X going in, and we get Y coming out. Okay, so this is the first of these stages. So this would be X1, this would be Y1, this would be Y2, and this would be YN. And as you can see, X and X1, so X2 is equal to Y1, isn't it? Because they're going into each other in kind of a serial fashion. Now it turns out through some mathematical jiggery-pokery, which people who are much more mathematically minded and intelligent than I am, they can do some kind of transforms on the formulae that go into all this stuff. And what comes out is an approximation which says that Y to the N is equal to, sorry, Y sub N is equal to some value A, which is multiplied into xn plus y of n minus 1 minus x sub n minus 1. So basically we're getting some addition and subtraction of samples here, and they're being multiplied by some value A. Now A, it turns out, is a value which is equal to, it's actually a fraction, and is 1 minus a value called WP over 1 plus WP. And what happens is we're going to constantly change. Each time we run through the buffer, we're going to change WP. So this value of A is going to change. It's going to sweep, and that means that the output here is going to change over time. So over the period of moving through the buffer, reading through the buffer, we're going to eventually, the A will change. So these values are going to change as well, and so Yn is going to change over time. Now WP as a value, I don't know why it's called WP. If anyone does know, then they could tell me. That'd be fantastic, because it's just everywhere I've seen it written down, it's just WP. This is the value of pi, told you it was mathematical, times a frequency, which we're going to call the bottom frequency, FB, and that's all divided by the sample rate. So the sample rate, remember, is a constant. In our case, that's 44,100. That's the number of samples per second that we're going to read, which is the CD quality sampling frequency, sampling rate. So that's basically the math. So we don't have to understand the math to make this, or to try and get this to work. But we have to kind of think about, though, is we've got a dry signal which is unadulterated. It's not been changed. We're going to grab some of that dry signal. We're going to pull it away. We're going to pass it through these n of these phase shifting filters. We're also going to take some of the output signal out and feed that back. So some proportion, some percentage of that's going to be fed back to the start to go through again in that cycle. And we're also going to be shifting omega period. It could be, I'm not sure what it is. It's some kind of, as you say, it looks like some kind of, it could be omega rather than W. And in the texts I've seen, they haven't, because they've been online, they haven't used. So XN is the input. So for one, for example, for stage one. So stage one, Y1 is going to equal to A times X1, which is the input. And obviously yn minus 1 and xn minus 1 are going to be 0 because we haven't got those values yet. So it's going to be that, and then y2, you just put that's going to be 2, that's going to be 2, that's going to be 1, and that's going to be a 1. Okay, so it's just the input. So x is the input into the stage, y is the output from the stage. And as you can see, that y1 is going to be the input into stage 2. So it gets a bit clearer when we do the code. So so frequency divided by sample rate could be thought of being a kind of a time, couldn't it? So omega is angular velocity, which can be expressed, I think, let's do a different, we don't get too bogged down with this, but the value omega, if we do that kind of a curly W, I think that's 2 pi f, isn't it? 2 pi times the frequency. I think that's it. So angular velocity. So remember, sine waves. Sine waves are all about. They can be generated by a point revolving around in a circle around a central point. So that's where these kind of angular velocity comes from, and why pi is involved, because we've got a circle. It basically being generated by a circle, and it turns out that you can generate any waveform at all by a composition, by adding sine waves together. So even kind of square waves and triangle waves and sawtooth waves can be built up by adding sine waves. And this is the whole concept of Fourier analysis, and the Fourier series is a sequence of sine waves. So that's where it all comes from, and that's why we can do what we're doing with all of our sounds. We can add them together because of these basic properties. Okay, but what I want you to kind of get from this is basically the idea that we are taking a signal which we're passing straight through. We're taking a proportion of that, some kind of proportion of that here. Comes the wet signal. It's going to go through n of these, and it's going to be the phase is going to be shifted as we go along. We're going to feed some of it back to amplify that effect, and then we're going to mix it all back into the signal. And the mix here is going to be it's important that we don't get clipping at that point when we mix it back in, which is why we're going to use a slightly more advanced function than the constrain function that I used on the chorus, and I'll probably go back and fix the constrain method as well, so that we use this new function. Okay, so let's actually write some code based on that. So this is where I need to check my notes. So I think I've gone through the first page of notes. So let's have a look what we need to do next. Okay. So we've got a number of properties which we're going to need to deal with. And we might as well get those properties down first. So we've got a float, which is going to be the dry mix. This is the percentage of the signal which is going to be left unchanged. That's our dry mix. We've got all equivalent. We've also got the equivalent, which is going to be the wet mix. Once again, the percentage of the or the proportion of the signal which we're going to actually push through the phaser. We've then got a feedback value as well, which is going to be basically a proportion of the signal, the wet signal, which we're going to feed back on itself and force to go through the whole kind of phase shifting process again and again and again. So it's a continuous loop. Then we need to have. So the other thing we're going to have is what I'm calling a bottom frequency. So it's a frequency which we're going to use for sweeping. If we go back to here, so it is this value here, f sub b. So f sub b is going to determine, obviously pi is a constant, our sample rate's a constant. It's going to determine WP. Okay, and then this will change. So WP will change, so A will change, and that's the idea where we get the sweep concept from. So that's going to be another floating point value, which is going to be our bottom frequency. I don't know if that's the right name, but that's what we're going to call it because I couldn't think of a better name. I think often they call it cutoff frequency because we're dealing with kind of filters, but it doesn't feel like a cutoff frequency. It feels like a base frequency, so that's why I call it bottom frequency. We're going to need to have once again a width. So we'll have width, which is our sweep width. So how far either side of our bottom frequency we're going to kind of stray. And we also need then we need a rate, sweep rate. So I'll call it sweep rate. This is very similar to the chorus. Whenever we're dealing with this idea of sweeping frequencies, so they change over time, backwards and forwards, it's like a low frequency oscillator basically. So oscillating that frequency, which is driving the change that we're implementing. Okay. So let's set some basic values up. So I've got some kind of starting values written down here. So if we say dry mix, we'll start that at 1. So 100% gets passed through, and the wet mix will be 100% as well. So basically, this is gain. So it's not actually percentage as such. It's the gain of the signal of the wet and the dry mix sources. So the signal can be multiplied by 1 and by 1. So it's not been reduced in gain. It's not been attenuated at all. By altering those values, though, we can kind of alter the mix of the dry and wet, and that should have different effects. Feedback. We're going to start off with a value of 0.2, which you could think of as 20% of the wet mix is going to be fed back on itself. You can think of it like that. I need to put a semicolon there. So it's the sweep rate. So this is basically hertz per second. So what's the change of the base frequency? How quickly is that going to change in kind of hertz per second? We'll start off basically with it's a low frequency oscillator, so we're going to start off at 1 hertz, but it's going to change by 1 hertz per second. I do apologise if this is getting too mathematical for you, but I'm afraid that's part and parcel of the subject. So if you kind of follow with me, And when we actually get to hear the sound, that's when we can enjoy it, and we can fiddle with the knobs and try and change the sound. So the bottom frequency, so the width, we'll start that off up to 1 as well. And the bottom frequency, it's not exactly a low frequency, but we're going to put it at 100 Hertz. So those are kind of starting figures I thought which would probably work for us. Okay, so we need to set. So if we go back over to our chorus sample, you can see that we have a set sweep method, and we're going to need the same kind of thing. We need to set what the sweep is going to be. Pardon me. And it's going to be a very similar kind of calculation. So let's do a set sweep method over here. So a lot of these concepts are very, very similar between different types of effect. Let's create we'll create a method there. Yeah. Okay, so this is going to be. So this is where we need, because the sweep is going to be as well as the sweep, we're going to change that WP or omega P, whatever that is. So let's just leave that undefined at the moment. The sweep is going to be basically affected by these 3 values. The bottom frequency, as we change that, we need to change the sweep. If we change the width, how far away from the center we're going to go, we need to change the sweep, and the sweep rate obviously is quite important for that. So let's expand these 2 properties. Part 2 vacuum field. Okay, so when we change these values, we're also going to want to set the sweep, because these are values which actually constitute the final sweep value. Okay, so we've configured those. These 3 values, however, they don't contribute to the sweep. They're actually just proportion of signal which we get, which goes through the kind of the setup we've got. Okay. So what we can now do is start to build the stages. So okay, so let's go over to, let's create a process method. Well, let's just show you what the read method is basically going to be. So this, we just need to get the samples from our source. So there's the source, and we're going to do the read method on that. Going to read those using the same values that we get passed into our read method, and then for each of those samples. So remember, the output of this is going to be an integer, a number of samples. Then we need to return that value. That's a count of samples. And here what we want to do is take the buffer and look at the offset plus I and we're going to process that buffer. So we need a process method. So we'll declare that. We're going to declare it. We'll declare it there. Okay. So we're going to pass a float value in. We'll call this the input sample. And we're going to return basically a float value back from that. Andrew, as for me, I'm a PhD in maths. It was a long time ago. Well, you can help me out then, Andrew. If you've got a PhD in mathematics, then I do occasionally dabble in maths. I've got quite a lot of mathematics textbooks upstairs on calculus and things like that, which I do enjoy dipping into. But it's been a long time for me as well, a long time since I did all that. So it's a lot of practice and a lot of revision really to get my kind of calc back up to scratch. Okay. So we need to first set up our value of A. So we're going to keep with the notation capital A. If you remember, this is 1 minus something called WP divided by 1 plus something called WP. And we don't want wave provider, we want WP. Oh, come on. Thank you. Okay. So let's have a formula here. We're going to say that A is equal to 1 minus WP. That's going to be a fraction. And then 1 plus WP. I'm assuming it is W sub P when they talk about this. Okay, so that is the calculation we're doing here. And we can say that W sub P is equal to a fraction of pi f sub b and it was, come on, thank you, it was S sub r, wasn't it? I called it. We need pi. Is it slash pi perhaps? Yeah. I've got S minus r rather than S sub r. Come on. There we go. So that's the mathematical formula for that. So the formula is CodeRush, Andrew. So it's CodeRush doing that. So these are we got an exception. What is that? So this is latex formulae in rich comments in CodeRush. So I have CodeRush installed, so you can see the CodeRush menu up here. So we can do all that kind of stuff. So I find that really quite useful to document what we're doing. Okay, so we've got WP, so we're going to need to do something with WP, aren't we? So we're going to need to have a private variable. This is going to be a variable which change. This is going to not. It's not a constant. It changes. So private float WP. Stick it up there. Okay. So that's our value of A. So our initial input. This is x1 in our diagram. If you remember our diagram, x1 is what goes in initially. Initial input is going to be the input sample. Okay, so it's the input sample. If we go back to our diagram, we're also going to be, so it's this what comes in here, but also going to be it's going to be multiplied by the percentage of our kind of a wet mix gain, and also it's going to have some feedback put into it. So we need to account for all those three things. Plus feedback. And the feedback is going to be multiplied by I'm not sure at the moment, but I think it's going to be the output of our yes, it's going to be the output. So times the output. So if you go back here, you see that the output here is being fed back, so we're multiplying by the output, and it's going back in. Did I call it feedback? Feedback. Thank you. And we need to define output. So we can define output. Just say return output at the bottom there. We'll have to work out what the output is. Stop it. What's it done there for? There we go. So we'll have to work out what the output's going to be, but that's going to be simply a chain. Now we're going to do the chain of processes. So, Linksumps, good evening, welcome. Yes, you've got your VIP badge. Enjoy it. Okay, catch your name is in the chat at all. Her gift subscription should have taken effect as well. So, catch your name if you're in the chat. Just type something into chat and we'll see if you're you should have a nice green rocket. Okay, good. I gave Catherine a gift sub because she was my 200th follower, so that was a reasonable reward, if that's such a thing. Okay, so now we're going into these boxes. So this is stage 1, stage 2, stage M. So we need to apply this mathematical equation to each of these boxes in turn. Once we've done one, the rest will become easy. So I'm just starting to not like having WP there. I want underscore WP. Okay. Let's just write out the equation. So it's going to be the stage 1 output is going to equal A times something minus something else. So the A times it's going to be the initial input So the initial input is going to be X, yeah, that's going to be going in, and we're going to get Y out. Y1 is going to be coming out. And then the equation, we've already put the equation up here as well, I suppose, haven't we? This is going to be Y sub N is equal to A C dot what was it? Where's my note? Where's my note? X of N plus Y sub N minus 1 minus X sub N minus 1. And that should be just about the end of the maths. We need to make that a bit smaller, I think. Yeah. Okay, so that's kind of that's the equation that we're trying to kind of push through. The initial input plus so it's going to be the output of stage 1. Minus the input of stage 1. And then we want to change the input to equal the initial input. So the next time around, it's taking stage 1 input and stage 1 output are going to initially be 0 because we haven't calculated them yet, and then they're going to we're going to move them along. So going to step through it becomes initial input. Okay, so let's define some of these values. Declare these up here. Stage 1. It's going to be a float. And input. Okay, so we need to decide how many stages we're going to have. Similar to text, yes, it's a latex. It's latex, Andrews. That's what they've implemented. I think it's really nice, especially as you can now have diagrams, also images in your comments. So, for example, that diagram, I could smarten it up and actually insert that into my comments as well. So, when you get complicated things like this, which your future self or people maintaining the program would benefit from having those formulae there, see what you're doing. So let's have so how this kind of setup works with the phaser is the more stages you have, the more kind of points of destructive and constructive interference of the sine waves or the waves that you have. So if you had, for example, 2 stages, you'd have 1 point of what they call a notch, 1 point where there's destructive interference. If you have 4, there'd be 2, 8, 4, that kind of thing. So let's have 8, and maybe at some point we could actually have a control where we could change the number of stages. So what I'll do is just copy this. We'll just have that many. So stage 2, stage 3, stage 4, stage 5, 6, 7, stage 8. Okay. And this stage output, which is the final output, it was what's going to get fed back in, isn't it? So it's not going to be output there, it's going to be stage 8 output. So whatever gets output, go back to our diagram, whatever comes out of here, it's got to go back, multiplied by the percentage, the feedback. It's got to go back and be mixed in with the wet input there, which is currently 100%, while the default value is set up. Okay, so now what we can do is just copy this down and say stage 2 oops, this is going to be stage 1 input. This is going to be stage 1 output. Remember, the output of one stage is the input into the next stage. This is going to be the stage 2 output, and this is going to be the stage 2 input. Something up here. Oh, that's small I, isn't it? I've got capital I's. I and I. Okay. Same here. What's wrong with that? There we go. Happy now? Okay, so that's 2 stages. Now we just increment these. So each one becomes 1 greater than it was last time. So now it's quite simple, isn't it? All we need to do is just rote copying, make sure we get all the values correct. Stage 3, stage 3. And now it's all incremented by 1 again. That's a 3. That's a 3. That's a 4. And that's a 4. So that's a 4-stage phaser. Let's go for 8 stages. Then we get the 4 notches. So this is going to be 5, 5, 5, 4. Let's hope this actually works at the end of this, because it's taken quite a bit of effort to actually understand it so far, hasn't it? And the kind of the payoff is it's actually having a decent effect at the end of it. Stage 6. That's 5. That's a 5. That's a 6. That's a 6. Maybe 7. This is going to be 8. This is going to be 6 and 7. 6, 7 and 7, and this is going to be 7, 8 and 8. So that's our 8 stages. So what's the output of that then? So we now need to mix the wet and dry set samples together. Okay, so what we could simply write would be it's a stage 8 output times the wet mix plus the input sample times the dry mix. But as was pointed out before, what this can result is that your amplitude exceeds 1 or -1, and we don't want that. We want to keep our values of our samples between plus and -1. Remember, they're 32-bit floating point numbers, and by convention, our waves' maximum amplitude is plus or -1. So, in the chorus sample provider, I had this constrain function. Where is it? Well, I said constrain the mixed signal. So it's exactly the same kind of idea. The mixed signal is some proportion of the input sample plus some proportion of the delayed sample. Exactly what we got. That's wet and dry. I put a constrain function on that says keep it between plus and minus 0.99. And it's simply that function. If the input's greater than 0.99, then it's 0.99. If it's less than minus 0.99, it's minus 0.99. Otherwise, put the output out. And as I pointed out last time, if we let's try and get a bit more. I don't think we can get any more room on here. But basically, if we have a different colour, it's a green colour. Maybe we can see that. That's basically going to be a function that's going to be like that. So it's going to be linear up until it gets to 0.99. Then it's going to say I'm outputting 0.99, and the same for the negative values. And ideally, what we'd like is to smooth that angle out so that it's more like that. So, I mean, there's a quick quiz question. We've got a PhD mathematics graduate in the house. What can we use to get that shape of wave? I won't keep it for long, don't worry. So, Pure Stable. Speaking of maths, you used to use Wolfram Online the other day to solve an equation system. You're rather pleased you figured you could do that because you're quickly getting bored doing it by hand. Yes, absolutely. So Wolfram, is that a maths package? There's several quite nice maths packages which are free, which I've used in the past, which are quite good. So obviously our pop quiz has not got any results, so I'm going to put the answer down. So we all know what a tangent is, yeah? The trigonometric function of a tan. This is going to be tan h, which is the hyperbolic tangent. So if we go and have a look at Wikipedia, hyperbolic tangent wiki. So I would never have guessed this. Obviously, I just think I've seen it in other algorithms. Graph. Here's Wolfram. So there you can see there's the hyperbolic tangent. You can see its maximum is 1, its minimum is -1, and obviously we got continuous number line through there. So we have a nice smooth transition rather than being angular. Then we get that transition there, which kind of softens out the it's Wolfram. Softens the clipping that's going on, or the correction to keep it within those plus and -1 constraints. So we're going to use that. Pardon me. So this is going to be math.tanh of that lot. I want a floating point number out of it because that gives a double. Okay. So we've now got our process sample, but the problem is we've got this fixed value of WP at the moment. We haven't actually give it a value at all. It's actually 0 at the moment. So this is A is going to be 1. We need to kind of cycle. We need to change WP based upon the sweep. So we're going to just multiply it by what we're going to call a sweep factor. So we multiply it by some factor which we've not yet defined. The kind of slight problem with that is if we multiply it by a factor, we need to make sure that it stays within certain bounds. So there's going to be a maximum and minimum that we want it, because we're going to oscillate between a maximum and minimum value. So we'll make sure it doesn't exceed that. So we just need to put a quick check in here. So if WP exceeds max WP, or its WP is less than min WP, then all we're going to do is say the sweep factor is equal to 1.0 divided by the sweep factor. We're just going to invert it. So we need to actually set some of these things up now, don't we? So let's declare this as a field. We'll declare it up the top here. Sweep factor, and we also had no, not property. Hit field. Let's go. This is going to be max WP and min WP. Okay, so we should have all the things we need to define there now. There should be underscores. Okay. So let's get to my notes again. So this is where we get slightly tricky. So we need to set these WP and the sweep factor up down here. So I'm going to write this from my notes. So this is not original code. Just bear in mind that if you need to actually write this kind of algorithm, then you're going to need help from the internet. Unless you really kind of understand the very basics of digital signal processing and the algorithms involved, you're not going to be able to generate these yourselves. So we'll start off by saying that when we set the sweep up here in set sweep, we're going to say WP is the same as WP minimum. Is it min WP? And that is going to equal to, remember that what we said WP was equal to, it's up here. WP is pi times the bottom frequency divided by the sample rate. So that's easy enough to do. So that's going to be math.pi times the bottom frequency divided by, so it's going to be the sample rate, which is the source.waveformat.sample rate. So that's going to give us a double, I think, so we need to make a float of that. There we go. So there's WP and WP min defined. So we need to have, we've got a value called width here. So width of sweep we're going to define that, and this is just out of the blue. It's going to be out the width that we entered, which is between 0 and 1, and we're going to simply add a number to that, and that number is going to be 6. Okay, we're just going to define it like that, and we can play with these numbers and figure out, if that has any effect. Then we can say that max WP is going to be the same as this. Except we're going to just add the width to that, the width of the sweep to it. So you can see that the min WP is going to be defined by the bottom frequency, and the max is going to be defined by so it's times the width. Thinking it's not plus the width. So we're just basically saying that we're going to have a nice 1 to 0 scale for our width, but we're going to actually, it's going to be, in reality, it's going to be 2 to 7 times the frequency. Okay, this is where it starts to get a bit more tricky. And the actual sweep rate, which is a value we're going to calculate, is actually going to be, so when you look into these algorithms, the sweep function is really quite important. It needs to be very smooth, and one of the best ways of having a nice smooth function like this. Source Goose, thank you for the raid. Welcome all raiders. Let's put some alfs in chat. There you go. Welcome all raiders from Source Goose Stream. Has been doing some digital audio work himself, I believe. Been working in a DAW. I've actually just got a DAW myself, so I've just downloaded Reaper. So I've been having fun playing with that with my new MIDI keyboard. How did it go then, Source Goose? Have you managed to make good progress on your project? Okay, so actual sweep rate. So we're going to use an exponential function for this, and it's, just take my word for it, the function we're going to use is this one. So we're going to take 10 to the power of the sweep rate, which is what we called the, do we call it sweep rate? I can't remember what we called it. Sweep rate, yeah. Divided by the sample rate. So that's source.waveformat.sample rate. And we need to make that into a floating point number. Into a float, that is. This is where it then starts to get a bit weird. So the algorithm that we're working to says we need to subtract 1 from that, and then we need to adjust it again. Actual sweep rate, we're going to multiply by 1.1, and then we're going to add 0.1. So someone has obviously sat down and fiddled with these numbers to get something which they think sounds good. Yes, so it's good. We're building a phaser effect for the synthesizer, so I'm hoping that we should be able to try it out very shortly. Now we can finally set our sweep factor. Our sweep factor, once again, a weird value, is going to be equal. This is going to be a float again. This is going to be math.pow. So this time it's going to be the width that we calculated just up here, the width of sweep, to the power of twice the actual sweep rate. There's a formula, but somebody's done it for us, luckily. And all this kind of information is available if you look hard enough on the interwebs. What's not so common is actually an explanation of what it's all about. Okay, so we should now compile. We should have all the bits and pieces we require. Okay, so we can get rid of that. Okay, let's just a quick run through. So we've got our basic parameters. There are 6 parameters that we need to control this. There's the dry and wet mix, the feedback percentage, the sweep rate, the width of sweep, the frequency we start from for our sweep, and we go backwards and forwards between that and something calculated from the width. We use these formulae. We've got an 8-stage phaser using this formula here on each of these stages, shifting the phase at each point, and then we use the hyperbolic tangent function to smooth out our output to make sure it's always between plus and minus 1 with a nice smooth curve. And then we step up our sweep factor here. We change the sweep factor every time we go through the buffer. Every time we process, we change it up, and we return the output. The output then is simply the new value of our sample. So the original sample gets transformed by process into a new value. So that should build as I say. Okay, we're now in a position to try it out. So we're just going to plug it in to the end of our sample, our signal chain. So let's have a private. This is going to be a phaser sample provider. Phaser. And we should now just be able to put it in after the chorus. So phaser is going to be a new. So we're not going to be able to control it yet, but we're just going to see what the sample of is. So this is going to be chorus going into it, and then instead of this being chorus, this will be the phaser going into the Fourier transform. Okay, so that's using these default values. Let's give it a go and see what it sounds like. Okay, so there we go. So it bombs straight away, doesn't it? So we got something wrong. Okay. So let's go through the notes. So 8 times that, initial output, inputs, stage 1 output, stage 1 input, that looks okay. Stage 2 output, stage 1 output, stage 2 output, stage 1 input. Stage 2 input equals stage 1 output, that's the problem. These should be outputs. Because the input of the next stage is the output of the prior stage, so that didn't make any sense to have it like that anyway. 7 output. Okay, let's see if that Okay. Let's play the note A. Oh, we're phasing. You can see it phasing. So it's that swirling sound, as if it's rotating. If I actually shift up the octave, and I play a chord. So you get quite complicated waveforms out of that. But with A, you can see it. Let's try it with some more some waveforms like a sawtooth with more high frequencies in it. Let's try it. It's a very synthesizer, isn't it? Try it with a square wave. Right. You get that phasing there. Triangle will be a bit smoother. So there we got a phaser. That's pretty good. What I'd like to be able to do is control all those various factors now. So what's the time? It's gone 11. Let's see if we can build a GUI which allows us to control those factors. So we've got space here to do our phaser. Okay. So we're going to stack panel in here. We don't need a name for it. And this is going to be where is our previous stack panel? That's in column 3, row 5. So this one's going to be in column 3, column 4. Yep, column 4. Okay. So let's reuse as much code as we can on this. So we can probably pinch those 3 items. That's 4 items. I'll pop them down here. So this needs to be in row 4. And we're going to have phaser. Okay, so now the values are so we're going to have dry and wet and feedback. Oops. And then we're going to have what else was there? There was sweep, width, sweep, and in fact what we'll do is just move this one up. This is going to be our frequency. frequency. So does that all fit on nicely? Invalid markup. Go back. Sweep. Feedback. Alright, I see. And we'll have our frequency there. Okay, that's that part of it. So there's another stat panel with some sliders in to have now. One day doing this will come a bit more naturally. Let's just format the document a bit. Where's it gone? There it is. Then we have another stat panel. Once again, we don't need a name. And this is going to have sliders in it, so let's go and pinch a slider. It'll be fine. So that's 1, 2, 3, 4, 5, 6 sliders. So the stat panel needs to be in the right place. So let's just move that into the right place. This is going to be in row 5. There they are. Princess, isn't there an iron triangle? Have I misspelt something? Where is Codebase Alpha? Codebase Alpha is in orbit around a black hole called Cygnus X1. Isn't where have a misspelt triangle? I'm notorious. Yes, there's an L in triangle. Let me go and correct that for you. Thank you for spotting that. That's in my waveform selector. Waveform, triangle. There's the octaves. Label, bold, sine, square, triangle. That's the radio button. Where is it? Name is triangle, content is triangle. Thank you very much, Princess, for spotting that for me. If you're a regular on this channel, you'll notice that I just make spelling mistakes all over the place. That's why I did have CodeRush in there to help me with that, but I don't think it's doing spell checks on me XAML, which is unfortunate. Okay. I'm also not an expert with XAML. You probably noticed. I'm very much a beginner with XAML. It's my very first WPF application. Okay, so we've got so this is going to be phaser dry, and that's going to be 1 and 0, correct. Phaser wet, phaser feedback. So feedback is going to go. It's going to create feedback. It's going to be in 0.05, and it's going to go. We don't want to feedback the whole signal, So we'll give that a maximum of. Actually, it'd be interesting to experiment with negative values as well. I've never thought of trying negative values in here. So next we've got this is the frequency, phaser frequency. Phaser width, and finally phaser sweep. So we need to just alter the margins a bit. The frequency needs to be changed as well, so that's going to be there's frequency. Yeah, so that's going to be, let's say 150. And we won't have any ticks on that. Every 10. Yeah, that'll be okay every 10. So let's sort these positions out. So the dry needs to go across a fair amount. So let's say it's going to cross 50. Nearly 55. Wet can come back. Feedback can go across a bit more. 25. Frequency 20. 25. Yep. And width and sweep look okay to me. So once again the spacing's a bit weird, but well, we don't worry about that so much. And now we need another stack panel. Oops. So this is going to be in it's going to be in. So this one was in row 5, column 4, row 6, column 4. Okay. So now we want some labels. So let's grab one of these. And pop these in. 4, 5, 6, and the width is going to be should be okay actually. No, the width is fine, it's too wide. So this one's going to be width 30, and we'll keep them at 30 for now. This is going to be phaser dry label, phaser wet label, phaser feedback label, phaser frequency label, phaser width, and phase sweep label. The frequency, let's make that 40. Let's see the positions of these things. So that needs to be brought across, say 60, 55. Okay. On here, margin is going to be 10. Margin 20, 25, 28. Yep. One here. 20, 25. Yep. This one here is going to be 25, 15, 12, and this one here is going to be 15, 20, 20. Yeah. Okay. That's the first rough GUI layout. We're going to need to remember what all these names are now. So let's go over to our T4 template. We've got a whole bunch of stuff to create. So we've got 6 more values to put in here. I'll just put them down. 1, 2, 3, 4, 5, 6. Let's just tidy all that up. So this is a real time saver. So thank you so much, FuelSnowball, for producing this template. It's fantastic. So we're going to have here phaser dry, phaser wet, phaser feedback, I can't remember anymore. Phaser frequency, width and sweep. Frick. Phaser width. Phaser sweep. Let's just tidy up. And then we just need to push these across. I think there's not much fiddling anyway, with a bit of fiddling with the frequency one. Oops. Me. So we can call that percent. Yeah, what we'll do is we'll do the same as we did here. No, we'll just leave it raw for the moment. We'll sort out the niceties of the GUI in a minute. Let's generate the template, generate the view model. Right, let's make sure that works. Make sure it compiles first. So now we should be able to move these around. We do. Okay. So we can't turn it off at the moment, but that's okay. We won't worry about that too much. So that's that built. Now we need to go over to our view model. Just set these changed up, these change partials up. So let's just change one first. This is going to be phaser dry. this is going to be phaser and phaser here. Phaser dry and dry mix. We should be able to copy this now. 1, 2, 3, 4, 5. This is going to be the wet. And the mix. Then there was the feedback. It's really a percentage, I guess. We can probably depict that as being a percentage. Then we've got phaser frequency. That's correct, and this is bottom frequency. And then we've got width. Fuel Snowball, it's a bit unfortunate you have to do double quotes for the label expressions, but you know, okay, it's not a, because I'm doing copy and paste programming, then it doesn't really mean, it doesn't matter to me. Once it's all set up, it's easy Fuel Snowball to kind of just use. I'm really pleased with it. Sweep. And this is going to be sweep rate, I think it's called, sweep rate. Okay. So now we get to control it. We need to better turn it off, but we can't turn it off at the moment, but we'll add that in a second. So at the moment, it's just going to be default. So it's going to be all zeros, isn't it? So there is a phasing effect. So let's say we're going to do that. We're going to put 20% of it through. The frequency is going to be 100. Width is going to be 0.2, and the sweep is going to be 0.5. I don't know. The clue is, can we actually make it change its sound different? Let's put a lot of feedback in. That's made a difference, hasn't it? Let's change the sweep. The width of the sweep and the rate. Change the octave. We're having quite a lot of different effects coming in now. It's not quicker. It's quite interesting, isn't it? But unfortunately you have to, oh sorry, you've already said, I've read that one out, Fuel Snowball, sorry. So we're having a fair amount of control over the sound there. It's let's try it with different waveforms, because that might be more. A lot of feedback. Yeah, lots of feedback. More generally, we can stick our low pass filter in then. We need a low pass filter at the end, on the end of the signal chain as well, I think, as well as at the beginning. Feedback. Yeah, we hit resonance then, didn't it? It went completely bonkers. So let's switch that off. Okay, so we need to be able to switch this feature off, don't we? So maybe if we go for the width of 0 again, maybe that's the control we need. So the sample provider, we'll just put in here and say that if width is less than 0.1, if it's greater than 0.0, then we'll do all this. Let's see if that gives us some control. We need to set some initial values as well, I think. Okay, let's get the initial values in on the constructor. That's over here. So actually, we could do this. We're doing the same for our chorus as well. So chorus, that chorus values up. Chorus delay equals 0.0f. Chorus sweep and chorus width. And then our phaser. Phaser wet. There's a feedback. It's a frequency. Let's do 0, so everything phaser width and phaser sweep. Okay. So we shouldn't now, if I play an A, we shouldn't have any. We got something there. What we got there? We've got some phasing going on, even though it's 0. Wow, that's a good name. Miel. Thank you very much for the follow. That's superb. Excellent. Thank you very much. That's very kind of you to follow. Okay, so we're not switching off our phasing, are we? Let's have a look what we got. So we set everything to 0. Oh, I guess what we're not doing is, we do got the control, haven't we? Set the controls. Phaser width equals phaser width. Okay, let's start it up again. Phaser sample provider. Let's start a note. Switch on. Width is 1. Try not setting those in the constructor. Switch on. A. I don't want that. Lower done. Oops, I've got to come in there. There we go. Okay, there's A. That's still phasing, isn't it? Width is 0. So it shouldn't be doing anything. Have we got another effect switch on or something? That sounds like a phaser. Oh, that's very interesting. Okay, let's try figure out why we're still getting. It's definitely skipping over. Set sweep. So the width is. Oh, that should be alright though. It's this width that's controlling it. So it's initialized all the values to 0. It's still phasing. Why is it doing that? Oh, there we go. It was chorus. We're getting some chorus, so these values weren't being initialized by the look of it. So now should. Okay. So we need to sort out why that was. I'll set the chorus width to 0. And the chorus samples here, probably need to remove any initialization here. So that's those initializations there, isn't it? Let's get rid of those. Okay, start it up again. Remote A. We're okay now. So if we put our chorus in, we'll give a bit of width, a bit of delay. So how similar do we think that chorus and phasing is? Get some artifacts in that one. Let's switch that off. So we definitely need a low pass filter. So let's put some phasering in. This is different, isn't it? So that's the chord of A with phasing on. Let's switch all that down and put some chorus in. It is different. It's a different effect. So if we have a longer delay on the chorus, so it's quite fun changing all these values. So let's just have another go with this. Let's have a high feedback, and we need to sort that out there. Slightly shopping. Yeah. So what happens if you have both? So let's sweep that as well. There's a lot of artifacts in that, isn't there? Can you? Yeah, so we need to sort out a low pass filter on the end of that, I think. So maybe we can do that now and see if that cuts out some of those weird artifacts that are coming into the. So doing a low pass filter is really quite simple because we've got a low pass filter class already. So let's just drop a low pass filter in towards the end of our signal chain. So let's have a private low pass filter sample provider LPF low pass filter low pass filter. What's its defaults? So its defaults are 4000 Hertz and with a Q and aggressiveness of 0.7. Let's try it with that and see what happens. We might need to raise that. It might cut a lot of our nice high frequencies out, but let's just whack that into the signal chain and see what happens. Where's our signal chain gone? Yeah. So phaser takes the chorus in, and then we're going to have a low pass filter. There's a new low pass filter. So that's going to be the phaser that goes into that. We're going to have a frequency of, I don't know, 20,000, which is the limit of human hearing, and then a Q will be okay, and then we'll put the low pass filter in here. Okay, let's give it a go. So it's not affected our pure sine waves. Let's put some chorus in. Some clicks and whistles in there. We probably need to try shaping our wave a bit. Let's have a bit of a slower attack. There's some beats going on. I don't know if that's beats or what. It's definitely a. I don't know if you can pick it up in chat. There's definitely something going on there. And that could be my sound card having trouble with all this, I suppose. Okay. Let's try some of this good source then. Of course, I'm just completely guessing. It's interesting to get. Let's put a low pass filter at the start of it. I wonder if we put everything on. Let's put a sub oscillator in there. We'll put some vibrato. We'll enable some amplitude modulation. We'll have some chorus. It's going to ruin it. This is where we could actually, it could blow up at this stage. So let's try an A. That sounds okay, doesn't it? So if you also have lots of fun doing dynamic colouring and effects based on time of day, yes, maybe we could have rather than kind of sample based effects, we could have what it feels like in the morning or the evening. That sounds pretty good. Wow. Good, drop an octave. Oh, we get some really computery sounds in that. Oh yeah, I like that. Wow. That's with everything enabled. Okay, so let's commit those changes. So that was added phaser and hooked it up to the GUI. So we commit that. Okay, so I think I've pretty much achieved what I planned to achieve, which is remarkable, really. So let's go and let's quickly go pop over to the issues list. So phase shift, and say we've done that. I did on stream. Close and comment. Okay. Chorus effect, we've wired that up. So we can close that one as well. I think there's more we can do with that one though, to be honest, but we might have a separate issue for what we could possibly do about sweeping the chorus a bit so that it's got some variation. Okay, so what we've got, we've got some other things. So we add instruments and preset voices. Well, that's going to be a while in the future, and that's actually more like actually these patches. There's something about here about create and record patches. So patches are going to be like presets. Sub oscillators, we've got sub oscillator in at the moment, but there was a question I had about can I add sub oscillators anything other than sine waves, and I still haven't looked at that yet. Graphic equalizer, I think Link Slumps was working on that, or at least he indicated he was going to. It doesn't matter if you don't ever finish that, Link Slumps, it's not a problem. So recording loops, which is something I'd like to do. Create and record patches, so we'll save them in, I don't know, JSON or something like that. Flanger, another kind of swirly effect. But I think the next thing we can start to look at is these more oscillators per note, and also the MIDI controller. So if you didn't see it before, I've purchased a miniature MIDI controller. So it'd be nice to get the MIDI features of N-Audio into our project, so I can play them on the keyboard. Rather than, so what we'll do is have a switch, so you can switch it between a MIDI controller and your computer keyboard. So if you haven't got a MIDI controller, you can still play around with the project. More oscillators. So this is what I'm thinking should be the next thing we look at. So on our GUI, I added the tab control at the top here. So what I'm thinking we should do is we would have on voice 2 and 3, we could probably have individual sound envelopes per oscillator, per voice, so you can juggle those around. Possibly the low pass filter. We'd certainly have a sine wave selector, and we'd also have a level, so we could have different levels. So main voice could be 100%, voice 2 50%, voice 3 25% of the amplitude contribution. And we wouldn't have a phaser or chorus. Those are kind of after effects. Same with tremolo and vibrato we might have. Double isolator we might have. We'd also want to be able to choose harmonics. So we might want to say that voice 1 is a sine wave at whatever, at the A3 octave. Voice 2 might be a sawtooth at twice the harmonic, twice the frequency. So I think we would want a voice level and a harmonic selector to go up here, and then on these we could just like not have these controls here. It should actually, if we switch on, actually I want the on-off buttons on all pages as well. I'll do that before we go. So it doesn't matter which page we're on, we can still see our visualizations. On-off buttons on all pages, but look at it once. Let's just quickly do that, and then we'll close. So these. You don't need a name for the stat panel. Not sure we need a name for the buttons. Let's stick this stat panel over here as well and see if that actually works. I don't know because I've disabled my very first WPF. So can we turn things on? We can. That's fine. Eventually they'll move into the right position, so it looks correct. Okay, that's good. We'll save that. Added on off buttons to all tabs. Okay, so I'm going to push this up to GitHub, where it'll be available for you to play with as you wish. Sync that up. My GitHub repository is here. Do feel free to browse the code, fork the code, and submit some PRs like Fuel Stable has. You could clone the repository and play with the code and change it and just call it your own, do whatever you want with it. There's other projects up there as well. The bot's up there that's running it in chat at the moment. So if you didn't know there was a bot, we have a little bot. So the project command tells you what we're doing. We've got a launches command which tells us about SpaceX rocket launches coming up. And then the big one is Falcon Heavy. Currently scheduled for 25th of June. That's going to be a night or evening or night launch. So it should be fantastic. This video will be archived to YouTube within 24 hours, and I have to wait 24 hours because that's the agreement I have with us being a Twitch affiliate. So you can go over to my my YouTube channel and see all previous 38 episodes. Do subscribe if you do go there. It helps me out. It's completely free for you to do so. If you want to join me on Discord, do go ahead. Here's the Discord invite. And also one of the ways you can be kept abreast of when I do broadcast is to hit that follow button if you haven't already, or to follow me on Twitter. And here's my Twitter account. Do follow at @CobaseAlpha on Twitter. It also helps me out an awful lot to get some reach, and also to promote other members of the Live Coders team, of which I'm a member. So we've I think about 50 of us now, live coders on Twitch, and we do all kinds of different types of coding and technology related streams. So there's pure coding streams like mine in .NET languages. There's also people who do other languages such as JavaScript, or we got Gareth Hubble who does C++ and Rust and F#. I do a little bit of F# along with Fuel Stable. We've got people who do Blazor. We've got people who do hardware projects, Internet of Things stuff, build keyboards. We've got one guy called Robert Tables who's building an AM radio on a Saturday. So lots of kind of hardware streams like that. There's a huge variety of live coding streams out there, and you're guaranteed of good quality if you follow someone on the Live Coders stream. But there are other people who are going to be joining the Live Coders team as well. So there's some fantastic streamers out there. So I can recommend a vast majority of them as being worthy of your attention. So do go and check them out. Thank you for viewing today. It's been a pleasure to work on that project with you. What I'm going to do now is try and find us someone to raid. So thank you for Sourcegoot and his raiders if they're still around. Let's see if we can find somebody else to raid. Who have we got here? Oh, we got Jitter Ted. We'll go and raid Jitter Ted, shall we? So do stay with us for Jitter Ted. So let's go. Oh, the Michael, is that the Michael that's hosting raid? Jitter. There with 37 viewers. So okay, so thank you very much. Thank you, Agent Coder, for the kind words. We'll see you again on Wednesday with the early show at 4 o'clock UK time, 3 o'clock in the evening, 3 o'clock in the afternoon UTC. We'll be doing some more work on the synthesizer. So do enjoy the rate, and I'll see you again soon. Take care, everyone.